Charles University is one of the CLS Infra partners hosting the Transnational Access Fellows. We participate as two departments, the Institute of the Czech National Corpus at the Faculty of Arts and the Institute of Formal and Applied Linguistics at the Faculty of Mathematics and Physics. Together, we specialize in corpus linguistics, computational linguistics, and natural language processing. In the CLS Infra project, we have also committed to evaluation and adaptation of the currently available NLP tools to digital humanities relevant domains. If you have textual data and seek help with processing them, then consider joining us for 3 months here in Prague. We prefer projects where we can help you answer your research question upon your textual data, where we would support you and mentor you through the process of building or editing or annotating and querying a corpus and basic descriptive or exploratory visualization of your results. And in return, we would like you to create a small data set where you would evaluate the performance of the tools you have used. You would resolve the task of the natural language processing tool in question manually, and then you would compare the performance of the tool when it works automatically. You would be the author of the released data set, and we would, of course, love you to be the co-author of a survey paper about the evaluation and adaptation of NLP tools to digital humanities research questions at the end of the project. With this series of transnational access stays, we hope to gather interesting experience with different languages, different genres, different historical stages of languages, different formats. And together with you, we would like to contribute to the community with the improvement of the mainstream tools. Let me show you in more detail how we would process your data together with you. Let me talk you through a mind map showing possible use cases in which we will gladly support you. In the digital humanities, textual data is often encoded in the XML TEI format. TEI, or TEI, stands for Text Encoding Initiative. This initiative has developed and maintains an XML standard for digital textual collections. The XML TEI allows you to encode many aspects of digital edition within one single digital document. For instance, metadata, typography, differences in print editions, orthographic normalizations, or glosses. XML TEI is very flexible to accommodate the immense diversity of humanities projects. This is both an advantage and a disadvantage. The advantage is obvious. The disadvantage is that different text collections fulfill the same standard by different means, and so it takes some effort to make them truly interoperable or to load them into a browsing or editing tool, be it one designed to be used with XML TEI data. XML TEI has been primarily designed for digital editions, and therefore it is somewhat difficult to incorporate rich linguistic annotations. If your research question on the text collection does not require information encoded in the XML TEI, work with plain text, and it will save you a lot of time and energy. However, sometimes you want to integrate your operations in XML TEI. For instance, when you want to display all layers of annotation together. Let us look at the possible layers you can add to a digital document with XML TEI. The heart of my mind map is an XML TEI encoded digital document. In our pipeline, we use a prototyped tool called TNA. You can, of course, use a bunch of different tools instead. TEI XML makes very much sense, especially when you want to preserve a connection between the machine-readable text form with a sound recording or facsimile image. Imagine, for instance, Project Gutenberg or the recently released LTEC, the multilingual corpus of 19th century novels. They are TEI XML encoded and available in digital archives, for instance, GitHub, from where you can download them and work with them. The XML TEI markup preserves some features of their printed originals, and their metadata contains information about the original, in this case, a concrete printed edition of a given novel. When you are building a spoken collection, you usually preserve the recordings and add transcriptions. There are several excellent open source transcription tools, such as Transcriber. When you are done working with Transcriber, you import its output into TNA. TNA converts these files to a TEI XML. When you have a collection of facsimile images, you will have to transform them into machine-readable texts. For print materials, we use optical character recognition tools. For very old historical prints and all handwritten documents, use handwritten text recognition tools, for instance, transcribers. This is a screenshot from transcribers. To the right-hand side of this image, you see the user interface. The tool has automatically recognized text segments. You can transcribe the text manually, line for line, down there, segment for segment. By manual transcription in this graphical user interface, you are linking the graphical segments to their textual counterparts. To the left, you see the resulting XML document with the linking and the transcription. When you manually transcribe about 50 pages, you can train an automatic recognition model tailored to the data you have. When you have finished the manual transcription, you export the transcripts, selecting the Page XML option, and import the Page XML files into TNA. TNA converts them into its TEI-conformant format. The TNA graphical user interface allows you both to edit the data and metadata of each file. Prior to starting your project, you set up your own metadata form. This is a metadata template of a correspondence collection listing the letter author, their instance in the virtual authority files, the date on and place in which the letter was written, and a few other details. The most important field is the language, if you want to have your text automatically tagged and parsed. The tagger looks in this field when selecting the corresponding language model. As a next step, you can edit the text. My demo shows a typo in a word Systematisierung instead of Systematisierung. Besides the typo, this example illustrates the so-called tokenization in TNA. The OCR or HTR transcription tools only recognize words as text segments between spaces. This word is divided by a hyphen in 2 lines. The tokenization in TATOC merges the 2 segments into 1 word for you, while preserving the information that it consists of 2 graphical elements. Words in tokenized documents are called tokens. Each token is a TXML element with a number of attributes which you can edit. The HTR tool, for instance, transcribers, identifies each graphical word as a rectangle of X and Y coordinates of pixels inside the facsimile image. These are automatic guesses. In TATOC, you can improve the rectangle manually. This is particularly useful if you consider importing the file from TATOC back to transcribers again, for instance, to train a transcription model. At this point, you have a TEI-conforming machine-readable text that you can view and search. However, if you are looking for the text content, you can only search for character strings seen in the data. You cannot easily extract content from all files at the same time. Imagine you would like to quickly extract events mentioned in your text. Events are usually expressed by verbs. Hence, you need a tool to indicate the part of speech of each token. With such a markup, you will be able to extract all verbs. Let's explore the options of linguistic markup then. This sort of linguistic markup is called morphological tagging. Morphological taggers often perform lemmatization along with assigning each token its appropriate morphological tag. The output of a tagger contains the original word forms, such as here the original Spanish text, the lemmas, and the tags. Sometimes, like here with the word del, the tagger notes a contraction of 2 tokens and lemmatizes and tags both components accordingly. Almost all languages for which corpora exist have their specific tag sets, originating mainly from the 1990s, which was the onset of truly big text corpora and their automatic processing. Major languages can even boast several tag sets. Until recently, you needed to learn the tag sets for all languages you wanted to work with. Not only do the traditional language-specific tag sets differ because of the structural differences between languages, but they can also differ in the granularity of detail and in their conception in general. For instance, the American Pentriban tag set uses 2 different tags for nouns in singular and in plural, while the Czech tag set employs a system of 15 positions of different morphological categories across parts of speech, with the irrelevant ones left empty. Let's look at the game changer, though, the universal dependencies. The universal dependencies, short UD, is a cross-lingual formal description of morphology and syntax and has gradually evolved into the current standard. Over 100 languages are represented among corpora using this formalism. Some of these corpora were manually annotated from scratch. Others were semi-manually converted from their original formats. This is very important since these corpora are used to train automatic tools on the given languages, and the bigger the data, the better their performance. The morphological description in universal dependencies consists of 2 sets of labels, the coarse part of speech tags and the more fine-grained morphological categories. There are 17 tags to describe parts of speech, including symbols, punctuation, and unresolved tags. The proper parts of speech are adjectives, adverbs, interjections, nouns, proper nouns, verbs, prepositions, auxiliary verbs, coordinating conjunctions, determiners, numerals, particles, pronouns, and subordinating conjunctions. These parts of speech are represented in all languages. Many parts of speech carry several morphological categories depending on language. So, for instance, English nouns express number through their singular and plural form. In languages with rich inflection, nouns carry more features such as case, gender, or animacy. UD calls these features universal feature. It is a system of attributes and values. The attributes and values are universal, but individual languages use only the relevant ones. For instance, these are the recognized values of gender in universal dependencies. It is common, which combines feminine and masculine, such as in Swedish. It's feminine, masculine, and neuter. The UD documentation is very worthwhile to read, since you can see how the authors have taken into account the differences between languages. Let's have a look at syntax description as well. Syntax is very useful when you want to extract information spreading across multiple tokens, and especially in languages with free word order. The universal dependencies represent each sentence as a dependency tree diagram with nodes and edges. Each token, including the punctuation, is represented by a node. Each child node has only one parent node. The edge between them represents their syntactic dependency relation. Each sentence has a technical root node, but the actual syntactic root node is the main predicate verb. Functional verbs, such as auxiliary verbs or articles, never have children, and they are governed by their content words. Each node contains a set of attributes and their values. The token form, lemma, part of speech, and features its own ID and the ID of its parent node, as well as the dependency relation it has to its parent. From this, you can conclude that the edge in the tree graph is a visualization of the node attributes deprel and head and carries no information on its own. And indeed, this is obvious from the plain text format of this annotation. When you forget about the lines starting with hash, you will see a table with rows and columns. Each row represents one token, and each column one UD attribute, as they are titled in the top row. ID, form, lemma, universal part of speech tag, the national or traditional part of speech tag, universal features, head, the ID of the head, dependency relation, and more. This format is called CONAL-U, after the CONAL Annual Conference on Computational Natural Language Learning, which organizes competitions in machine learning in NLP and has been using this tabular format ever since. The U at the end indicates that it is the universal dependencies flavor of the CONAL format. These are the 37 labels for dependency relations. The most basic ones are nominal versus clausal subject, or various types of objects, attributes, and adverbials. The logic of the labels is comprehensively described in the UD documentation. This rich annotation is provided by UD Pipe, a multilingual UD tagger and parser developed at the Institute of Formal and Applied Linguistics. If you want to run its online demo with your own data, go to the department websites, Research, Tools, UD Pipe 2, and select the appropriate language model and just hit the Run button. You will obtain the ConnellU file to download, its prettified HTML layout to read on the spot, and interactive tree graphs for all sentences, which you can download as SVG files. You may come with a language or language variety for which UD Pipe has had too little or no data. Some languages are represented by very small corpora or corpora that are not representative of the common language use, for instance, only newswires or Wikipedia. Such corpora do not contain first and second person in verbs, just to illustrate that this is a fundamental problem when your data comes from a different domain than the data UD Pipe was trained on. The same goes for older texts. Language models trained on modern texts are going to be confused by archaic orthography or inflection forms. In such cases, you have several options. Run a different tool on your texts if you know that it is going to perform better. If it does not use the UD tags, but some language-specific ones, create a simple spreadsheet with your labels and map them on the UD labels. Then TATOC is going to show you the UD tags instead. Or you use the best suited UD model and obtain data with many errors in the annotation. You correct it manually and upload it on GitHub among the other corpora. When your data contain about 5,000 tokens, it is usually enough to either create a dedicated model or substantially enhance an already existing model with that. A new version of UD Pipe is released every 6 months, and the developers train models of all corpora in their GitHub repository that are large enough. In an older build of UD Pipe, the user can easily train the model themselves anytime. The same option is soon to be added to the current UD Pipe 2 as well. In any case, you ought to manually verify the quality of the linguistic markup, be it just to evaluate the performance of the given tool for your research. You can use a range of editors, for instance, TATOC itself, or Thread, or Inception, or more recently, Arborator. You can manually correct the automatic annotation straight in TATOC. You can hang a node on a different parent, or you can change the dependency label of a given node. Or you can edit any other attribute of a selected token node. While TATOC is useful if you need to keep working with a TE-XML file, it is often more comfortable to use dedicated large-scale annotation tools. This is a screenshot of Thread, a tree editor with which the department's flagship corpora have been created. It takes a ConnellU file on input and returns a ConnellU file on output. You can easily search in and navigate between sentences in a sentence list, as well as use numerous keyboard shortcuts to edit node attributes. The great strength of this tool is its powerful query language with which you can find problematic positions. However, You cannot bulk edit them. Also, Thread is not being further developed. It has been maintained and still works, but you may encounter problems with, for instance, missing Perl libraries on your computer, which you need to install manually, and many other unpredictable things. Thread is excellent once you make it work for you. Meanwhile, modern annotation tools have been developed elsewhere. This is a screenshot of Inception, a successor of WebAnno, developed at the Technical University in Darmstadt, Germany. And this is Arborator, another new tool, still pretty much in development. It is collaborative and works in the web browser. To sum up, to enrich your text with morphological and syntactic analysis, use a tool, manually evaluate its performance on 5,000 tokens, and if you are not happy with the results, help train a more appropriate language model by providing your manual annotation to the developers. In our case, we are talking about UD-Pipe and UD-Corpora, but the same applies to other tools and other formalisms if you want to stick to a language-specific annotation scheme instead of using the multilingual standard. The main purpose of the linguistic annotation is information extraction. Naturally, you need a query language to extract phenomena you are interested in. The most common query language for textual corpora is CQL, the Corpus Query Language, developed at the Institute for Maschinelle Sprachbearbeitung in Stuttgart in the 1990s. This has become a standard for morphologically tagged corpora. However, it was not designed for tree searches. Several tree query languages have been developed, mostly along with a syntactic annotation scheme, in many projects for many different languages. This is still a pain that there is no universal tree query language, and none of the currently available querying tools is perfect. TTOC currently provides two almost identical flavors of CQL for linear search and two tree query languages, Prague Markup Language Tree Query, PMLTQ, and GRU Match. Let us explore the linear search with the Corpus Query language first. The first implementation is the Corpus Query Workbench, originally developed in Stuttgart. Its core, the Corpus Query processor, not only finds text snippets that match a CQL search, but can compute aggregated statistics on them, such as occurrences. The Corpus Query processor is used by many other corpus management programs, such as Context. Context is the tool used by the Czech National Corpus. Apart from concordance search, it computes various collocation measures for you. All in all, the corpus management programs, based on the Corpus Query processor, use the same language, but they differ in the range of computation on the matching concordances. The PMLTQ and GRU search are two query languages and tools for tree diagrams. Both are declarative languages. This means that your query draws a template of the subtrees you want to find, with conditions on the nodes. For instance, you can search for a subtree consisting of a verb as a parent and a noun as a child. The PMLT query was originally designed for the complex multi-layered annotation of the Prague dependency tree banks. It is an extremely powerful query language in which you can both find subtrees with complex conditions and extract results in a tabular format with so-called filters. You will find details with examples in the tutorial. This is a screenshot of a PMLTQ search for a subtree consisting of a node called chance, which has a child called attrib. The chance node must have the lemma chance and should be in singular. The node attrib should fulfill the following conditions. Its dependency relation, attribute deprel, must either be an attributive clause or anything else with a deprel label saying that it is an attribute, or a determiner, or a head of a noun compound. Then when it is a determiner, it should not be the indefinite or definite article. When it is a non-clausal attribute, it should not be an adverbial attribute, for instance, fortunately or surprisingly. The adverbial attribute could correctly occur there under some very special circumstances, but we will consider it noise and effectively limit the search to the remaining dependency labels containing the string mod, which would return a mod, n mod, and num mod, adjective modifier, noun modifier, and numeral modifier. This query would get us, when we hitting this button without filters, will return these concordancies with the nodes in question marked in colors. The part of the query after this arrow is the so-called filter. If you run PMLTQ without it, you will obtain the concordancies. If you use it, this button execute query, you will obtain filtered results as you define them. In this case, the filter says, give me from the node attrib its deprel, its part of speech, and its lemma. These are going to be 3 columns in the filter table, 1, 2, 3, and give me the count of each combination of deprel, part of speech, and lemma. So this would be a 4th column with no name. And then please sort the rows according to the first column, which was the deprel column. And when there are ties, then sort them according to the second column, part of speech. So here, all of this part of the table are ACL, and they are so the parts of speech are alphabetically sorted. And this is the GRU match query language, which is quite new. It has a different syntax. Here is an example. And might not have some functions of PMLTQ. Unlike PMLTQ, it has a replace function, so you can rewrite trees with rules. It has a very nice and comprehensive online tutorial. Now we go back to Tato. Using CQL, you can bulk edit or multi-edit tokens. For instance, if you find out that a word has been systematically tagged in a wrong way, you can find and replace all occurrences with the correct tag. In Tato, you can also directly annotate named entities and link them to databases such as VIAF or Wikidata. This is a screenshot of manual named entity annotation in Tato. Here I have shown you that we can support you in projects that involve small, high-quality data sets that you want to browse and edit at the same time, and you want to be able to store them in XML-TI. We will be particularly glad to support you in using, evaluating, and creating morphosyntactic annotation, but we can guide you through the entire workflow from transcripts to an XML-TI conforming corpus.